Hello, everyone. In this lesson, we'll be diving into the world of turning processing using ZW3D. Our course is divided into 5 main sections: feature definition, parameter settings, lathe tool, operation introduction, and case learning. ZW3D offers intelligent and user-friendly functions that will guide you through the turning process with ease. You'll be up and running in no time, and we'll have you proficient in just 1 hour. Let's get started. Before we jump into our learning journey, there are 2 important points to remember before creating a turning toolpath. First, ensure that the x-axis of the global coordinate system aligns with the turning axis, and the origin should be positioned on the right side of the part, just like in the picture shown below. Second, when working with turning operations, the most common feature is the profile. It's composed of a closed loop of wireframes or an open counterclockwise wireframe. This wireframe loop represents the outline of the part, and when you're creating the feature in the CAM environment, make sure the profiles type is set to part. These key points will set the foundation for successful turning processing in ZW3D. Based on the second point mentioned earlier, when we intend to create the profile feature for turning operations, we need to start in the CAD environment by using the planar section command to extract the profile lines based on the XY plane. Next, you can hide the solid part, leaving only the profile lines, and using the axis line as a boundary, retain only half of the profile lines. This is because the turning process is based on generating toolpaths from just 1/2 of the profile lines. Once you've completed processing the profile, you can move on to the CAM environment to create the profile feature. Let me emphasize this once more: if the profile lines are closed, the direction can be either clockwise or counterclockwise. However, if the profile lines are open, the direction must be counterclockwise, or else the toolpath won't be generated. Isn't it straightforward to define the features for turning operations? We only need to remember those 2 key points we discussed earlier. Alright, let's move on to the second part: parameter settings. The parameters involved in turning operations are similar to those in 2x and 3x milling. They consist of primary parameters, limiting parameters, tolerance and steps, path setting, link and lead. Next, we'll go through the key and commonly used parameter settings one by one. First, let's quickly review the purposes of these major parameter categories. Primary are used for setting the custom coordinate system and features. Tool and speed/feed are used to manage the tool and set its parameters. Limiting are used to define the cutting region, which includes the limiting edges such as right, left, top, and bottom. Tolerance and steps are used to define path tolerances, stock thickness, step values, and the number of cuts, among other things. Path setting are used to define cutting regions, cut directions, safe distances, and point settings. Link and lead are used to define the parameters for leading in and leading out. Display are used to define the width and color of the toolpath. Let's take a look at the primary parameters, including frame, feature, tool, speed, and feed settings. They are quite similar to 2D and 3D milling, but in turning, there's one important thing to keep in mind. When you're creating a CAM file, make sure to use the default turn template. Otherwise, you'll need to manually create a new frame and select the YZ plane. Both methods will ultimately give you the ZX coordinates for turning. Please note that in the first method, the turning coordinates will be automatically activated, while in the second method, you'll need to manually activate them. You can do this by right-clicking on the frame and selecting Set Active. The cutting range is a feature that restricts the tool's cutting area, including 4 directions: right, left, top, and bottom. Let's take a look at the differences in the 3 images. The one on the left has no trim planes set, the middle one has trim planes set on the left and right, and the one on the right has trim planes set on the top and bottom. Once these are set, the toolpath won't generate outside of the trim planes. Clearance angle is used to specify the offset angle between the cutting edge and the stock, including the main and deputy edge. In most cases, you can use the default parameters without any issues. In this slide, the cutting range parameters applies exclusively to threading operations. The cut position is used to pinpoint the exact location of the thread. To do this, click the Cut Position button to select a point from the part profile, and the line that includes the selected point becomes the machining area. Start length allows you to set an offset distance at the beginning. No toolpath will be created in this area. For thread length, you specify the entire length of the thread. Please note that if the user sets it to 0 or null, the toolpath will be automatically generated based on the total length of the thread, as shown in the figure in the upper left corner. Path tolerance. The default value is 0.01. Smaller values make the actual toolpath closer to the ideal toolpath. Facing thick. This is available in facing operations and controls the thickness of the remaining stock on the face. Axial thick and radial thick. These are available in rough and finish operations and control the machining allowance along the Z or X axis. Step value. This sets the distance for each toolpath's cutting. Number of cuts. This defines the number of toolpaths. Step type. This is only available in groove operations and specifies the step size, including the percentage of tool width and the absolute value of the step. PEC control is a feature that's exclusive to groove operations. When you select Yes for PEC control, it enables two additional options, PEC depth and retract offset. You can use PEC depth to specify how deep each PEC goes until the tool reaches the desired depth for rough grooving. Retract offset allows you to define the distance the tool backs up before making another PEC. The parameter on this slide is also applicable in threading operations. The thread depth represents the distance between the crest and root on each side measured perpendicular to the lathe's Z-axis. Cut type is divided into three types. Constant. This means that the depth of each cut remains the same until the rough threading is completed. Percent remain. This is a percentage of the remaining rough threading depth. It implies that as you get closer to the bottom, the cutting depth becomes smaller. Min depth. You can specify the minimum depth for the rough cut. In the fifth part of our course, we'll focus on the main parameters of path setting. However, it's important to note that the parameters for path setting can vary significantly in each operation. So, in this section, we'll go through the key toolpath parameters for each operation. Let's begin with the drill operation. In this operation, there are 5 commonly used parameters. They are return distance, clearance Z, dwell time, and tool home. Return distance refers to the distance above the top of the hole from which the drilling motion into the hole will begin. Clearance Z is used to specify the engage distance, which is the space above the hole where the tool can safely move. Dwell time allows you to specify how long the tool remains at the bottom of the hole before it retracts. The default time unit is seconds. Tool home is used to specify the place the tool located before and after drilling. These parameters are essential for configuring the drilling operation effectively. The second one is facing path setting. In this context, there are also 3 commonly used parameters. Cut direction is used to specify the tool's movement direction. You can choose to machine the workpiece from right to left or from left to right. Overlap refers to the distance that the tool cuts beyond the center of the part's face. Station point is used to specify the tool's starting and ending locations. You can either input coordinate values or click the Station Point button to select a point. For motion type, you have the options of direct, axial radial, or radial axial. Now, let's move on to the toolpath setting parameters for the rough operation. There are a total of 9 commonly used parameters. The first one is cut region, which can be divided into OD and ID. This parameter is used to choose the machining location, either on the outside or inside of the workpiece. Next is cut direction, which is used to specify the tool's movement direction. You can have the tool move from right to left or from left to right. Drill diameter is used to specify the diameter of the hole, and the toolpath will not be generated in this area. You can see the difference between these two figures. For cut strategy, you have three options: cutting along the horizontal direction, vertical direction, or the profile of the part's direction. When it comes into concave, this parameter allows you to control whether the tool enters concave areas that are not part of the flat face. And for clearance, this option is only activated when you set into concave to yes. It's used to specify the vertical distance at which the tool begins machining the concave areas. These parameters play a vital role in defining how the roughing operation proceeds. Tracking point allows you to choose the tracking point for the turning tool, which affects the generation of the toolpath. It's important to note that users must first add the tracking point in the tool manager, and then it can be selected from the drop-down menu. For shallow corner, you can specify the cutting toolpath style and profile corner. There are two options available: extend and round. However, please keep in mind that this parameter only controls the corner style for the last toolpath. Output type provides support for two options: custom way and cycle way. You can compare the differences between these options in the following illustrations. This slide is all about finish path settings. When it comes to tool compensation, there are 5 modes to consider. In computer mode, the toolpaths will receive compensation when they're being calculated. In control mode, there won't be any compensation, and it will output G42. For the other 3 modes, please refer to the accompanying text description. Now, let's talk about safe distance. This is the distance you set between the toolpath of one layer and the toolpath of the next layer once the turning process is completed. Lastly, we have cut reverse. This feature allows you to reverse the machining direction without altering the shape of the toolpath. This slide covers the essential parameters for groove path settings, and there are 12 key parameters to focus on. Cut strategy is the first one. It offers 3 ways to generate the groove toolpath: zig, zigzag, and alternate. It's important to note that when the Enable Level Control option is set to No, zigzag is essentially the same as zig in terms of the cutting toolpath style. Relief amount refers to the distance that's defined from the tool to the side of the groove after it retracts. Stock height lets you specify the amount of extra material left above the top of the groove before the rough turning process begins. Let's continue with the remaining parameters for groove path settings. Rough clearance allows you to specify the height above the right vertex of the groove. Safe distance comes into play when you have more than 2 grooves that need to be machined. This value helps prevent the tool from colliding with the part during path linking. The tool will move up to the safe distance and then horizontally to the next groove. Enable Level Control is a setting that determines whether to use level grooving or not. When you check yes, the toolpaths for layered grooves will be generated as shown in the description. Level depth allows you to set the cutting depth for each level of grooving. Let's dive into the finish groove settings, excluding rough cut settings. Users can select yes/no/ only to control whether to use the finish grooving after the rough grooving or separate finish cutting groove. When you select yes, the rough and finish toolpaths will be generated together. If you choose no, only the rough toolpath is generated. If you click only the finish toolpath is generated. Finish thick lets you specify the stock thickness that remains in the lathe's X and Z axes once the finish grooving is completed. Retract position is the parameter that specifies the axial distance from the retract beginning position to the right vertex for the first finish pass. If the input value is shorter than the actual tool width, the finish grooving will machine the groove only once. otherwise, it will machine twice. Based on the 3 images below, we recommend the setup on the right. This is because when we set the retract position, the tool will first lift away from the sidewall and then move down along the sidewall. This machining method is safer. Back-off distance is used to specify the retract width for the finish grooving, which is the axial distance between the beginning and end points of the retract. Please note that this parameter takes effect only when the second pass of finish grooving exists. Overlap allows you to specify the recut distance between the first finish pass and the second, if it exists. This parameter becomes effective only when the retract position is wider than the tool width. Here are the threading path settings explained. Number of springs lets you choose the number of starting points for the thread. The default value is 1, which means a single thread start. If you want a multi-start thread, you can adjust this value accordingly. Hand of thread determines the rotation direction of the thread. You can select either left hand or right hand rotation. Pitch is the measurement of the distance between 2 adjacent teeth on the same location of the thread. It's essentially the gap between the threads. Pull-out lens specifies how far the tool should move away from the end of the thread before retracting. Finish depth indicates the total amount of material left on the surface for finishing the threading. If you enter a value of 0, it means the groove bottom is machined directly. Number of finish, you can input a value here to determine how many passes the cutting tool should make to achieve the desired finish depth. This setting determines the number of times the tool will cut the thread to reach the specified depth. The final operation is part off, and let's take a look at its path settings. Part off point, click the cut off point button to choose a point on the workpiece outline profile. The tool will make a straight cut on the workpiece starting from the selected point. Cutting depth, you can set how deep the cut should be. If you select yes, the cutting depth can be customized, but it must stay within the limits of the tool size. If you choose no, the maximum cutting depth is determined by the size of the tool. Geometry corner allows you to specify the shape of the corner of the part, such as whether it should have a chamfer or a fillet. Next, we will discuss the parameter settings related to lathe tools, including subtype, insert, holder, tracking point, and speed/feed. In the Tool Manager, there are 3 subtypes: turning, grooving, and threading. Turning is used for facing, rough, and finish operations. Grooving is specifically used for groove operations. Threading is intended for threading operation. For each tool, you can configure the following parameters: insert, holder, tracking point, speed/feed. Let's start with insert. This parameter is used to specify the geometric characteristics of the lathe tool's insert. The options in the dialog depend on the selected tool subtype, which can be turning, grooving, or threading. As a helpful tip, you can place the tool in the model space and observe how the tool's shape changes in real time as you adjust these parameters. The second parameter is holder, and it is used to define the geometric characteristics of the lathe tool shank. The options in the dialog for this parameter depend on the selected subtype of the tool. Please refer to the lathe tool size figure and adjust the parameters accordingly. For speed/feed, it's worth noting that you can set different speeds and feeds for the same tool. Simply click Add to include another set of speed and feed values. This is more convenient than before, especially if you need to use different speeds for various machining operations. Regarding tracking point, due to the rounded corners at the tool tip, the contact position between the turning tool and the workpiece changes during actual machining. On the imaginary circle formed by the center and radius of the tool tip arc, there are 9 tracking points available, as shown in the figure below. By selecting different tracking points for calculation, you can achieve different turning tool paths. We've just gone through the primary parameters for each machining operation. Now, let's explore the various turning operations available in ZW3D. From the ribbon interface, You can see that there are a total of 7 turning operations in ZW3D. Drill is used to drill holes in turning. The toolpath is displayed in the figure. Facing is used to machine the face of the workpiece. Rough is designed to remove as much excess material as possible. Finish is used to cut away the remaining allowance left by the roughing operation. The remaining turning operations in ZW3D are as follows. Threading is used to machine threads on the workpiece. Groove is used to cut grooves on the workpiece. Part off is used to separate the desired part from the workpiece in the final step. Alright, we've covered the theoretical knowledge, and now we'll walk through the entire process of turning programming using a real example. First, we need to do some preparatory work, such as adding the stock material, defining the coordinate system, and specifying the features, among other things. Next, we'll create the required tools based on the needs of different operations. Here's a tip. When you add a tool while creating an operation, the software will automatically match the appropriate tool type. For example, if you're creating a groove toolpath, it will select the groove tool type. Then, based on the profile features, we'll create operations. We'll use verify and solid verify to ensure that the toolpaths are reasonable. Finally, after making sure that all operations are correct, logical, and efficient, we'll define the machine and generate the NC code. Now, let's open the software and try to complete a turning program together. Hello, everyone. In this chapter, we're going to guide you through the process of turning with a simple example. First, the geometry is already in the right spot. What we need to do is get the contour of the part. Here's how you do it. Use the planar section command to get the whole section of the part. Make sure the plane is set to XY, with an offset of 0. Hide the part and delete any unnecessary curves. The profile feature in turning only needs half of the part's contour. Okay, now let's switch to the CAM environment. Here we should choose the turning template. The coordinate system is already set up for typical turning situations, so no need to adjust it manually. This is the turning coordinate system. Now, let's create a profile feature. Select all the lines and click OK. Just a quick reminder, if the contour isn't closed, set reverse direction to yes, to make sure the toolpath is generated correctly. But in this case, the contour is closed, so we just leave it at default. Finally, let's set up the stock. Add the stock material and configure the parameters as needed. Well, let's start with the facing operation to remove the excess material from the top. Select the profile feature you want to use for this. Next, define the tool you'll be using. You can see that the lathe type is corresponding to the operation type. Just click OK and go on. You can place the tool in the environment and check out its shape, which is automatically adjusted by the parameter. But for now, just stick with the default settings. Now, in the Primary tab, keep the speeds and feeds as they are. No need to change those settings. For tolerance and steps, leave the path tolerance at the default settings. Set facing thick to 0, number of cuts to 2, step value to 1. This means that the tool will cut the stock twice, 1 mm for each time, and there will be no remaining materials left after this operation is done. Moving to the Path Setting tab, set cut direction to right to left, overlap to 0.5, and pick the station point as you like. This means that the tool will cut from right to left, starting from and getting back to the station point as you picked. And when the tool reaches the center of the part, it will continue cutting 0.5 millimeters deeper. Now, calculate the tool path and verify it to ensure everything is set up correctly. Next, we'll start with the rough turning operation to remove as much material as possible. Add the profile in the feature. You can use the same tool as used for facing. For this operation, we're focusing on axial thickness and radial thickness, which should both be set to 0.2. Also, set the step value to 2. This means the tool will cut 2 millimeters of material in each pass, leaving a 0.2 millimeters allowance along the axial and radial directions after machining. Optionally, you can set a cut range for the toolpath generation. Click on the right trim plane and select a point to define the limitation. Do the same for the left trim plane. Now, let's configure the path settings. In the Path Setting tab, set Cut Regions to OD, Cut Direction to right to left, Cut Strategy to horizontal, and into concave to NO. Also, pick the same station point as used in the facing operation. We just need to copy the one we used in the previous operation. This means that the tool will cut the outside surface of the part from right to left. The tool paths will be horizontal, and it won't cut into concave areas. For the link and lead settings, set Extend Distance, Lead Out, to 6. This means the tool will continue cutting 6 millimeters before retracting. Now, calculate the tool path. After roughing, the next step is to create the finish turning operation to remove the remaining material left by the rough turning operation. Click the Finish button and add the same profile feature and tool as used in the rough turning operation. Set axial thickness and radial thickness to 0. This means that there will be no remaining material left after the finish operation is completed. Next, we'll set some necessary parameters as we set in rough turning operation. In the Path Setting tab, set Cut Reverse to NO and Tool Compensation to Computer. Keep the other settings the same as in the rough operation. This means that the tool will cut the outside surface of the part from right to left with compensation and will not cut into concave areas. Calculate the tool path and verify it to ensure that everything is configured correctly. The next step is to cut the grooves on the part. Click on Groove and add the same profile. Define a new tool for grooving. You can place the tool in the environment and set the insert width as 4, which should match the width of the grooves. Be sure not to make the width larger than the actual groove width. Then we define the parameters. Set rough thickness to 0.2. Enable PEC to NO. This means that there will be 0.2 millimeters of material left after rough cutting. In the Path Setting tab, set Cut Strategy to Zigzag. Set Finish Groove to Yes. This means the tool will cut the grooves in a zigzag pattern for the tool path and will enable a finish cut after roughing. Calculate the tool path. Now, let's take a look at this through simulation. You can see that the tool path is below the part, and the tool entry is also below the part, which is not safe. So, we can divide these grooves into 2 regions for optimization, and the improved tool path will be more reasonable. We'll add top and bottom trim planes as restrictions here. This way, we can retain the upper portion of the tool path. Next, we'll create another new groove operation to machine the bottom of this groove. Select the top and bottom trim planes, calculate to see the tool path, and modify the stock height to 11. Calculate the tool path again. Now the tool will enter from above to ensure safe machining. In order to demonstrate all the turning operations, we assume that there are threads on the right cylinder of the part. Click Threading and add Profile feature. Create a new tool and define the parameters, just set as default. For options in Limiting tab, specify cut position here, and set start length to 0, thread length to 0 or null. This means that threads will start from the selected point. ZW3D will automatically calculate the thread length. For options in Path Setting tab, set number of spring to 1, hand of thread to right hand, pitch to 2, finish depth to 0.1 and number of finish to 1. In the Link and Lead tab, set both. Extend distance to 2. This means that cutting will start 2 mm earlier before entering the part and continue cutting 2 mm after finishing the part. Now, we should machine this hole. Before starting a drill operation, it's important to gather hole information in advance, including the diameter, depth, etc. Click on Drill and add the Profile feature. Define the tool and set cutting diameter as 8 mm. Set drill type to peck drill, depth to 18, depth reference to holder and leave hole start to null. This means that the drilling is a peck type, and the distance from the beginning point to the tool holder is 18 mm. ZW3D will automatically find the start point of drilling. For options in Path Setting tab, set return distance to 3, dwell time to 0, and tool home start/end to station point same as previous operations. Keep others as default. This means that the drilling will start and end at the same point as the station point. Calculate the tool path. Next, use part-off operation to separate the objective from the workpiece. In this operation, user can generate toolpath by defining a cutoff point. Click on Part-off and add Profile feature. Then we create a new tool for this operation. Place the tool in the environment and you may notice that the tool length is not sufficient for the cut. To address this, switch to the holder interface and adjust the shank line and insert extension. Select the right end as the cutoff point and the same station point as previous. Calculate the toolpath. Up to this point, all the operations have been set up completely. It's recommended to check all the toolpaths using Solid Verify after calculation. Here's how to do it. Right-click on the text operations in CAM Manager and select Solid Verify. Click the play button to start the simulation. Ensure that all areas have been machined properly. Next we go to define the machine. Double-click here and select ZW Turning FANUC. Double-click Output to create a new NC file. Right-click to call out the setting dialog box. Then define the output file location. Right-click on Text NC and select Add Operations to include all the operations we have created. After that, let's output the NC file. Thank you for your valuable time. In this video, we've walked you through the entire workflow for turning operations. Now, I encourage you to try creating your own turning toolpaths following the course.